Okay, so what you do is that you have your sample. We have our sample container here. Let's say this is something. This is either urine, or this is blood, or this is spit, or something. And then we might have done an ion exchange already. We might have done some kind of separation already, but we might not have. And so what we're going to do is we're going to take our syringe and we're going to take a little bit out of that sample. So here's our syringe. I'm going to draw a syringe. And then we're going to take that syringe and we're going to put it in an instrument that's called high pressure liquid chromatograph. And so what we're going to do is perform high pressure liquid chromatography. And so we're going to pass this sample through a pump onto a solid phase. And the drug molecules are going to interact. So these are drug molecules. So we're going to take our syringe that's going to have our sample. So from our sample, we're going to have all kinds of different metabolites. We're going to have metabolites from whatever food you ate, from different processes as your organs grow and change, as things die in your body, etc. There's going to be all those kind of waste products or different products that are going to be available or existing in the biological sample. So they're going to be available for analysis. And so what we're going to do is we have that syringe and there's going to be all kinds of, different sugars and aldehydes and all these different things. And we're going to have to figure out how to separate them. And so the way that we're going to separate them is we're going to use chromatography. And so the chromatography we use is going to vary, but basically what happens is that we're going to have some kind of solid support and we're going to pass our mixture of chemicals over this solid support. And this solid support is going to have the property of interacting with each of the chemicals in the mixture with a different affinity. And because of that, we can separate the mixtures or the chemicals in our mixed sample into individual chemicals because they are going to interact with that solid support with a mixed or different affinities for each different chemical. Does that make sense? Hopefully it does. And so what will happen is that let's say that in that syringe we had a mixture of chemicals that here I'm drawing like stars and moons and squares, but they're all going to interact with that solid phase differently so that as I pass more solvent over the solid phase after I've set up that initial interaction with the solid phase, I'm going to pass more solvent through, and each of these molecules that was in my initial metabolite sample is going to dissolve back into the solvent at a different time. So I syringe the sample into the instrument, then I'm going to pump solvent through. And so what I'm going to get is I'm going to get a readout as each of my chemicals come out of the instrument. So I have that mixture, and so the readout is going to give me peaks. So I'm going to have a detector. And my detector is going to detect peaks. And so one of these peaks is going to be the star, we'll say. One of them is going to be the moon, and one of them is going to be the square. But I don't know that yet. I just know that I have peaks. And so I need to figure out what those peaks are. And so the way that I do that, since those peaks could not be a lot of sample, they could be less than a nanogram of sample, the the way that I'm probably going to want to do that is using mass spec, because mass spec is a lot more sensitive than something like NMR. And so it's got a higher sensitivity, and so that's why I'm going to use that. So what I'm going to do is I'm going to take each of those samples there, and I'm going to collect each of these peaks into different vials. So now each of my individual components of that initial sample are in individual sample vials. So we'll say they're new samples for my next analysis. So what I'm going to do is I'm going to have a vial that's from peak A. So this is peak A. So now I have a vial that's A. I'm going to have a vial that's B. And I'm going to have a vial that's C. And so what I'm going to do is I'm going to take this vial. So let's say I'm going to take a syringe, and I'm going to take some of the liquid that's in, say, vial C. So I'm going to take my syringe again, and I'm going to put it in a mass spec. And so what a mass spectrometer does is it's going to ionize the compound that's in all the compounds that are in the mixture in it, and it's going to run them through an electric field, and based on their molecular weight, that will determine how far they fly in the electric field. So what it does is it makes it so all the molecules are charged the same. They have the same charge. It runs them through the electric field, so the only thing that's going to matter is their mass. So what happens is I'm going to put this into, let's say we'll syringe it again, and then I'm going to put this into a mass spec. And so I'm going to ionize. So I'm going to put it into a mass spectrometry instrument. And the first thing that's going to happen inside the instrument is that it's going to ionize the molecules. So let's say they all have +1 charge. And then I'm going to shoot the molecules into an electric field. So I'm going to shoot those molecules into an electric field. Now, since they all have the same charge, they're going to fly through the electric field, and the only thing that's going to affect how far they fly through their field, their trajectory, is their molecular weight. So they all got the same momentum. They all got the same charge, they all got the same initial force on them. The initial force on them is going to be the same. And so the only thing that they have that's different is going to be their mass, right? And so the heavier molecules are going to land first, and the lighter molecules are going to fly farther in the electric field. But in this case, we'll say that my sample was really pure, so we only have one molecule that's going to fly right through. And what's going to happen from this is that I'm going to get a mass. So this detector in the mass spec is going to give me a mass. This is going to give me a mass of the metabolite. So what I'm probably going to have to do is take this mass, and I'm going to have to run another mass spec on it. So I have this mass. So this is going to correspond to the molecular weight of my metabolite. But if I want to know something about the structure, because a lot of molecules have the same molecular weight, then what I'm going to do is I'm going to take that initial mass, that initial sample, and I'm going to run it through mass spec that whole mass spec process, I'm going to run it through again. And I'm going to use higher ionization this time. Let's say, use stronger ionization. Etc. So I'm going to use a stronger ionization method. I'm going to do a couple other things to electric field. And what I'm going to find is I'm going to take that initial mass, and that mass is going to be broken up into little fragments because of the ionization energy. So I'm going to break the initial mass into fragment mass. And those fragments are characteristic for different molecular structures. So based on the molecular weights of the fragments, I could probably say, oh, I think that's an amide, I think that's a methyl group, etc., etc. And that gives me an idea of the structure. And so this is a way to use two mass specs to give you a tandem mass spec. So it's a mass spec followed by another mass spec on that peak to give you some structural information about that initial peak. And combining that with the data from the LC, the liquid chromatography that we did before, that allows you to identify that, okay, yes, this single peak here, this sample C is the molecule I'm calling square, because it has the molecular weight of square, and when I break it apart, its connectivity is the same as what I would expect for square. There's 3 methyl groups, there's an amide, there's blah, 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 blah. And so that is how they do that. So they'll do that again and again, because you can imagine they're going to have a lot of different peaks here. And so they have databases of this information that they can cross-list or cross-reference with. And you can actually, we can access this too as academic scientists. And so that's how that is done.